Hi, Chem 151 students, and welcome back as we continue our discussion of thermodynamics. So in the last thermodynamics video, we introduced the concept of entropy, and most importantly, the second law of thermodynamics, which states that a process such as a chemical reaction or a physical process will only be spontaneous if the total entropy of the universe, or in other words, the entropy of a system and its surroundings, which includes the rest of the universe, is increasing. And so we would say that a reaction is spontaneous if the total change in entropy, or delta S, is positive. And then we related that to a new quantity called delta G, which is easier to measure and allows us to determine if a chemical reaction is spontaneous based on delta G, rather than trying to measure the change of entropy in the entire universe. So this delta G, or the change in Gibbs free energy for a process, is defined as the negative of the temperature times the total change in entropy, or the change in entropy for the entire universe. And so if that change in entropy for the entire universe is positive, that indicates a spontaneous process. Thus, if delta S is positive, that means negative T delta S is negative. Therefore, delta G is negative. So a reaction or other physical process is spontaneous if the total change in entropy for the universe is positive, or if the delta G for the reaction is negative. And so here we have this equation: delta G equals delta H, the change in entropy or heat energy at a constant pressure, minus T times delta S for the system. So all of these, they don't have system written underneath. Usually we leave out system because it's understood. So here delta G becomes much easier to measure than the change in entropy, because it focuses just on the system we're interested in rather than the entire universe. And so that's why we try to determine delta G instead of the change in entropy for the universe, in order to determine if a reaction is spontaneous or not. We can determine delta G based on the change in enthalpy for the reaction, or delta H, and the change in entropy for the reaction, or delta S. A reaction is spontaneous only if the delta S total, or also called the delta S of the universe, or this could also be called the system and the surroundings, is positive. And so when delta S total is positive, that means delta G is negative or less than 0. So if delta G, or change in Gibbs free energy for a reaction, is less than 0, we say the reaction is spontaneous. If the delta G is positive, we say the reaction is non-spontaneous. It will not occur on its own. And if delta G is 0, that means the reaction is neither spontaneous nor non-spontaneous. It means that it is an equilibrium. It will neither go in the forward direction or in the reverse direction. And then based on that, we summarized the various situations based on the delta H of the reaction and the delta S of the reaction, whether the reaction would be spontaneous or not. If a reaction is exothermic, meaning the delta H is negative, and the reaction is increasing in entropy, meaning the delta S is positive, then based on the formula here, if delta H is negative and delta S is positive, meaning the second term is negative, then delta G must be negative here in this situation, and so the reaction would be spontaneous in all circumstances. If the reaction is endothermic, meaning the delta H is positive, and it is decreasing in entropy, meaning the delta S is negative, that would cause the delta G to be positive according to this equation, because the first term would be positive, and because delta S is negative, a negative of a negative is a positive, so the second term would also be positive. So for an endothermic reaction with decreasing entropy, that reaction will be always non-spontaneous at any temperature. Now, if a reaction is exothermic, that favors spontaneity. It makes the term more negative here. But if delta S is decreasing in entropy, that is unfavorable to spontaneity. It causes the second term to be positive because the negative of a negative is a positive. So then whether the reaction is spontaneous or not depends on the size of the delta H term versus the T delta S term. If the delta H term is larger, since it's negative, that will cause delta G to be also negative. However, if the T delta S term is larger, that term is positive if delta S is negative, and so that will cause the reaction to be non-spontaneous. So the reaction will be non-spontaneous when temperature is large, because that will cause the second term to be large and positive, and that will cause delta G to be positive. It will be spontaneous at low temperatures, because at low temperatures this second term will be small and the negative delta H term will dominate, which will cause delta G to be negative. If a reaction is endothermic with increasing entropy, the endothermicity of the reaction makes it contributes to non-spontaneity. However, the increasing entropy favors spontaneity. So here, the second term, because the delta S is positive, the second term here would be negative, and so a large second term would lead to a negative delta G. So this, when delta S is positive, the reaction will be spontaneous if the temperature is high, because the T delta S term will be bigger than the delta H term and it will be negative. However, the reaction will be non-spontaneous if the temperature is low, because then the positive delta H term will dominate and the delta G will be positive, indicating a non-spontaneous reaction. So this is an essential concept in thermodynamics. This is a question that I can guarantee you will see. You've already seen it in a quiz. I like to ask it on the final, and also you will see it as a part of your ACS final exam as well, which covers all of general chemistry. Then the last topic that I covered in the previous lecture was the idea of the standard state. And so in the appendices of your textbook, you are given delta G of formation, delta H of formation, and entropy values at the standard state. And the standard state specifically means 1 atmosphere pressure of all reactants and products, and 1 molar concentration for substances if they are in solution. For the temperature, it usually means 25 degrees Celsius, but not necessarily. In the appendices of your textbook, it does indicate that it's saying temperatures of 25 degrees Celsius or 298 Kelvin. So we had the equation delta G equals delta H minus T delta S. A more specific version of that equation is delta G standard equals delta H standard minus T delta S standard, because this would be for the very specific state situation where all of these are at standard states: 1 atmosphere pressure for all reactants and products, 1 molar concentration for all substances in solution. So this equation is relevant when all gases are 1 atmosphere pressure, all aqueous substances are 1 molar in concentration, and it's a more specific form of our general equation that we derived earlier, delta G equals delta H minus T delta S. Note that delta G is not the same as delta G standard. It's more general. Delta G standard is specifically under these conditions. Delta G are any conditions that happen to be present at the time. So any pressure of gases or any concentrations of aqueous substances. Same for the delta H and the delta S. Standard is a specific state. However, we define this specific state because it allows us to make nice tables like the ones in the back of your book that apply to the standard states. Then we can find the situation for the non-standard states by adjusting from there. So this applies at all concentrations of pressures, whether they be standard or not. And again, yeah, these standard values can be found in Appendix B of your textbook. For reactions that occur at temperatures other than 25 degrees Celsius, you can use this equation if you simply plug in the temperature that's not 25 degrees Celsius. And the reason why is because delta H and delta S are not as temperature dependent as delta G. And so it is an approximation. They do change with temperature, but not very much. So we can approximate a delta G or a delta G standard or a delta G by plugging in the temperature, whether it's 25 degrees Celsius or not. I do want to say is that I have a slight. I just noticed this. The tables in the back of your book give delta G and delta H of formation values for substances. If you wish to find the delta G or the delta H of the reaction, you do so in the way that we discussed previously with the product delta G's or delta H's multiplied by the coefficients in their balanced equation minus the reactants multiplied by their coefficients in the balanced equation. Okay. So this question says, calculate the standard free energy change at 25 degrees Celsius for the Haber synthesis of ammonia, whose equation is given right here, given the standard enthalpy change for the reaction and the standard entropy change for the reaction. And so we're going to use the equation delta G standard equals delta H minus standard minus T delta S standard. But you have to be very careful when you apply any of these equations. The reason being is that entropy values are generally given in the units of joules per Kelvin. However, delta H values are given in kilojoules. The most common mistake for these problems is to not make sure your units are consistent. So since you're in my class and I'm your teacher, I'm going to insist you write your units in your calculations so that you don't make this horrible mistake. If you're writing your units, you will notice when joules and kilojoules do not match. If you don't write your units, that's the way you make mistakes. Keep your units. I know it's a pain, but it's going to save you. So let's do that. First of all, delta S standard is in joules. We can either turn these kilojoules to joules or we can turn the joules to kilojoules. I'm going to take this 198.7 joules per Kelvin and I'm going to turn it to kilojoules per Kelvin. And the reason why I'm going to turn it to kilojoules is because delta G values are generally convenient in kilojoule amounts. And so I like to change the entropies to kilojoules when I'm trying to get free energy changes, delta G changes, or delta H's and so forth. So we're going to change the joules to kilojoules. So we're going to use a conversion factor that 1,000 joules is 1 kilojoule. So I'm going to put the 1,000 joules on the bottom so that the joules will cancel, and I'll put the 1 kilojoules on the top. So now my joules cancel, and so I'm going to do negative 198.7 divided by 1,000, so that gives me negative 0.1987, and my units are kilojoules on the top and kelvins on the bottom. Now we're ready to plug into delta G standard equals delta H standard minus T delta S standard. So we've got our delta H standard in kilojoules, it's right here. We've got our delta S standards in kilojoules, it's right here. The one other thing you have to be careful of is temperature. Temperature has to be in Kelvin. You won't forget if you keep writing your unit Kelvin here. So 25 degrees Celsius in Kelvin, you add 273, that is 298 degrees Celsius. So that's what we're going to use, or sorry, 298 Kelvin. So that's what we're going to use here. So we're going to make sure the temperature is in Kelvin. Make sure your units cancel, please. This is how you do physics and chemistry right. You will get it right if you follow what I tell you. Keep your units. That's what got me through grad school. Anyway, so we're going to plug in our delta H. It's right here, negative 92.2 kilojoules. We're going to subtract temperature times delta S. So the temperature is 25 degrees Celsius, which is 298 Kelvin. And our delta S standard here is the negative 1.987 kilojoules per Kelvin. So you can see here, because you kept your units, you can watch the kelvins cancel. And now you're going to be adding kilojoules with kilojoules. You can add kilojoules with kilojoules. So now let's plug this into our calculator and calculate this. So this is going to be negative 92.2 0.2 kilojoules minus the quantity 298 times negative 0.1987, close parentheses, and we get negative, let's see, and this should be to 1 after the decimal. That will be our limit here, so it's going to be negative 33.0 kilojoules. Negative 33.0 kilojoules is what we get. Okay, and so that's how you find the delta G from delta H and delta S. And if it were a different temperature, you plug in whatever temperature it is and you can estimate the delta G. Of course, again, the delta H standard and delta S standard values I've given you here, they apply to the standard state and they happen to be at 25 degrees Celsius, but you can estimate delta G by plugging in a different temperature if the temperature is different, because delta H and delta S don't change as much with temperature as delta G does. It's essentially, there's a small amount of error, but it's acceptable there. Now, if you want to find the delta G of the reaction in a different way, fortunately in your book, you are given delta G of formation values. And remember, formation means the formation of a compound from the elements in their standard states. And I'd like to pull up, just to remind you guys of how these are defined. Remember, there are no zero values, no natural zero values for delta, for Gibbs free energies and for enthalpies. What we do is we compare the enthalpies and the Gibbs free energies of substances to one another, and that's the way that we make these charts. Now I have uploaded for you both this week that I've given you here both the thermodynamic appendix and the electrochemistry appendix, which we'll use soon. So here are the thermodynamic values. Notice we get delta H's of formation and delta G's of formation, and for elements in their standard states, those are 0, because again, for elements in their standard states, they're defined as 0. We compare the energies and the enthalpies of compounds relative to the elements that form them in their standard states. And so for any element in their standard state, it's going to be 0, and the rest is going to have a value here. Notice that for S standards, none of these are 0, and that's because all of these are for 298 Kelvin, and entropy is different. There is a defined 0 for entropy. It's for a perfect solid crystal at 0 Kelvin. None of these are at 0 Kelvin, so all of the entropies are greater than 0, and a negative standard entropy is not possible. Okay, so to find the delta G of a reaction, we find it in the same way we would find the delta H of a reaction given the table we have here, or the delta S of a reaction. We add up the delta G's of formation of products multiplied by their coefficients in the balanced equation, and we subtract the delta G's of formation of reactants multiplied by their coefficients in the balanced equation. So if we have two products here, it will be the coefficient times the delta G of formation of product C plus the coefficient in the balanced equation times the delta G of formation of product D minus the sum here of the coefficient for reactant A times the delta G of formation for reactant A plus the coefficient for reactant B times the delta G of formation of that reactant. And here are some delta G of formation values. Notice again, for elements in their standard state, such as hydrogen gas, nitrogen gas, they are 0. Carbon graphite is the standard state of carbon. Its delta G of formation is defined as 0. Remember, just to remind you, because people often get confused about formation, if we're talking about the delta G of formation of acetylene right here, that is the delta G of, or let's do it. That would be the delta G of formation from carbon graphite, because that is the standard state for carbon, and hydrogen gas, that is the standard state for hydrogen, H2 gas, making 1, it's very important that is a 1 mole of C2H2 gas, and this happens to be a gas. So here we would balance this with a 2 to have 2 carbons, and there would be a 1 here. And so the delta G of this reaction, the delta G standard specifically of this reaction, is the delta G of formation of acetylene gas. Okay, and our equation still applies here, because if we wanted to find the delta G of this reaction, it would be the delta G of formation of acetylene minus 0 plus 0, because we define the elements to have 0 delta G. So just a reminder of what formation means. The delta G of formation is the delta G of the reaction that forms 1 mole of a particular compound from the elements in their standard states, which are defined to have delta G's of formation of 0. Same applies for delta H's. It's a little different for entropies, as we discussed. So let's do a problem where we calculate the delta G of formation for a reaction from the values in the appendix. And so we've got this reaction here. Iron, let's see, it's iron 3 oxide reacts with 3 carbon monoxide molecules, makes 2 moles of iron, solid iron, and 3 moles of carbon dioxide gas. So we would go to the appendix and look up the delta G's. And to calculate the delta G, we're going to do the delta G of the products here. So 2 times the delta G of formation of iron, plus 3, because there's a 3 here, times the delta G of formation of carbon dioxide gas, minus the reactants, minus 1 times the delta G of formation of iron 3 oxide, plus 3 times, because there's a 3 here, the delta G of formation of carbon monoxide gas. I will remind you, if we look these up, let's go ahead and look back at the appendix. I'm going to go to CO2. Notice that there are different delta G's of formation here for CO2 gas versus CO2 aqueous versus CO2 solid. The delta G's of formation will depend on what state of matter the substance is in. And so we're specifically, for example, if we're looking for CO2 gas, we're looking for this one, negative 393.5, not this one, negative 412.9. So using this table to look up these values, for iron, of course, it would be 0 because it's an element in its standard state. For carbon dioxide, it'll be negative 393.5. And I have 394.4 here, which is slightly different. I may have looked it up from a different table. There are some little differences here, but close enough. We'll take this one then. And then looking up from the same table, we're going to do minus 1 times the delta G of formation of iron 3 oxide solid. If you look that up, it's negative 742.2 kilojoules per mole, plus 3 times the delta G of formation of carbon monoxide gas, negative 137.2 kilojoules per mole. And now we're ready to plug this into our calculator. So obviously we don't have to do 2 times 0 here. That's just going to be 0. So we're going to do here 3 times negative 394.4. And then we're going to do minus the quantity, because we need to add these together first. 1 times negative 742.2 plus 3 times negative 137.2. Close the parentheses. And I get here negative 29.4, and my units are kilojoules per mole, or kilojoules. Now another point about this thing, kilojoules per mole versus kilojoules. So this is very commonly confusing for students. I know it was for me. If we've got 2 moles here and the moles cancel and the moles are all canceling, you might say, okay, we'll just write kilojoules here. But sometimes people will write kilojoules per mole. And either one is acceptable. What we're saying when we say per mole, we mean when every 1 mole of iron 3 oxide reacts, the delta G for that is negative 29.4 kilojoules. Or when 3 moles of carbon monoxide react, the delta G standard for that is, in this reaction, is negative 29.4 kilojoules. So it means a lot of different things. It means negative 29.4 kilojoules per 1 mole of iron 3 oxide, right here, because there's a 1 right here, not written. Or it also means, if we're talking about carbon dioxide, it means negative 29 rather 0.4 kilojoules per 3 moles of CO2 that are produced in this reaction. So that's the way that you translate what you have calculated here. So that's why sometimes people don't write the mole. It's because the mole there is also implied, and sometimes people write the mole. It's just to say that, you know, it relates here to what you see in this equation. When 1 mole of iron 3 oxide reacts, delta G for that is negative 29.4 in this reaction. Or when 3 moles of CO react, the delta G for that is negative 29.4 kilojoules. That's the way you translate what that means and what you've calculated there. And so you can write this as either negative 29.4 kilojoules and the mole is implied, or you can write negative 29.4 kilojoules per mole. But I know that's often confusing for students, and it was for me, because it looks like the moles cancel, and they do, but often people write per mole so that they can tell you, yes, I specifically mean, I'm referring, you know, per however many moles are indicated in this equation. Now, at this point, we've calculated delta G standards, and the value of these appendices, like, you know, like the one you see here with all these delta G standard values, the delta G standard of formation, is that they allow us to calculate the delta G standard of any reaction if we have these tables. But what about if the conditions are not standard, which is, you know, to be honest, most of the time, it's kind of a rare situation that you've got 1 atmosphere pressure of all gaseous products and reactants, or 1 molar concentration of all aqueous reactants and products. That's kind of a very specific situation. So what we do is we have an equation here that allows us to adjust for the actual delta G for non-standard state conditions. So we calculate the delta G standard just like we just did, and then we apply this term RT ln Q in order to make an adjustment to apply it to the delta G and determine the delta G of non-standard conditions. So remember what Q means. Remember Q and K, we learned about that before. You would determine the Q here and then plug that in, and then that will allow you to find the delta G of the reaction in non-standard conditions. So here the R, it's important to remember, is the thermodynamic R. So it's the one that involves joules, and so that's 8.314 joules per mole per Kelvin. And the temperature, of course, must be in kelvins because of the R here. Also, the R is in joules, so be careful. There's another situation where the ideal constant is stated in joules, but your delta G standard is probably going to be in kilojoules. So you're going to probably want to convert this to kilojoules when you actually use it. So for delta G, to get the free energy change under non-standard conditions, for this equation and all thermodynamic equations, Q and K are going to be special too. They're called the thermodynamic Q or the thermodynamic K. They will be different if you have gases versus if you have aqueous substances. For all gases, you're going to write down the amount inside the Q or the K of the pressure in atmospheres. So you're going to use the pressure in atmospheres for gases. However, for aqueous things, you're going to use the concentrations in molarities. So what you calculate depends on whether you have gases or whether you have aqueous substances. If you have gases, you're essentially calculating the QP and the KP in terms of pressure. However, if you have aqueous substances, you're calculating the QC or the KC, the Q or K in terms of concentrations. So here, if we're again talking about the Haber synthesis of ammonia, generating ammonia from nitrogen and hydrogen, Q here is going to be QP, because all of these are gases. So we're going to be wanting to put the pressure of gases in atmospheres in our calculation of Q. And so QP for this reaction would be, again, products over reactants. So it would be the pressure of ammonia squared, since there's a 2 on top, the partial pressure of ammonia squared because of this 2, then divide by the reactants. It's going to be nitrogen, the pressure of nitrogen to the first power, times the pressure of hydrogen cubed, since there's a 3 here on the bottom. So this is old stuff from chapter 17 about how to calculate Q and K. The only thing that's new in thermodynamics is that for gases you need to use the QP, and for aqueous things you need to use the QC. And same goes for K. So here we want to calculate the delta G standard for a reaction. It's the formation of ethylene, C2H4, from carbon and hydrogen at 25 degrees Celsius when the partial pressures are 100 atmospheres of hydrogen and 0.10 atmospheres of ethylene. Okay, notice carbon is a solid here. Okay, so just like all Q's and K's, we don't include pure solids or pure liquids, only gaseous things and aqueous things. Okay, now the delta G standard for this reaction is equal to the delta G of formation of C2H4. It is 68.1 kilojoules. Think about why. These are the elements in their standard states. So this is the formation reaction for ethylene. Let me see if these values are still the same. It's actually delta G of formation. Here we go. 68.36 right there. Yeah, is the delta G of formation. So that's 68.1, close enough there. It's a little bit different. I think when I wrote this, I was using a slightly different table there, but the values are close enough there. They're within the right number of sig figs there. So now we're going to calculate the delta G for this reaction, but we need to have Q, because delta G is going to be delta G standard, like you see here, plus RT ln Q. We're going to use this equation. So we need to get Q. So QP is going to be product concentration, the pressure of, product pressure, because they're gases, C2H4 on top, divided by the pressure of H2 squared. We don't include the carbon in the Q because it's pure solid. We don't include pure solids and liquids, only gaseous and aqueous. So let's plug in those values now. It's 0.1 atmospheres for the pressure of C2H4. So we're going to calculate the ln Q here. So ln of Q. So the Q here is the pressure of C2H4 on top. It's 0.1 atmospheres, so we put it here. And the pressure of H2 on the bottom, which is 100 atmospheres, and we square it. We put it on the bottom there. So let's calculate the ln Q part now. So that's going to be the natural log of 0.1 divided by 100 squared. And that's going to equal to us negative 11.51. Negative 11.51. Writing this with 2 after the decimal because we have 2 sig figs. This should really be 3 sig figs. I should have put a decimal point behind it. So we have the ln Q now. Now we can plug this into the equation. What I'm going to do is I'm going to carry forward the values I have on this slide to the next slide here. So ln Q is going to be 11.51. Delta G standard is 68.1 kilojoules. So we're going to use delta G equals delta G standard plus RT ln Q. And from the last side, we have ln Q is 11.51. No units there. Delta G standard is 68.1 kilojoules per mole. And R is always the same thing, 8.314 joules per mole Kelvin. Now you're going to notice something. The delta G values in kilojoules, but the R values in joules. We need to find a way to get these consistent, right? Watch out. This is the common mistake in this problem. I see it all the time. Especially happens when people don't write their units. Write your units, please. So we're going to have to convert either delta G standard to joules or R to kilojoules. Delta G is probably going to be more convenient in kilojoules, but it does make a kind of small R, which is inconvenient. It's really up to you. What I'm going to do is I'm going to convert my delta G standard in kilojoules. I'm going to convert it to joules. Okay, so 1 kilojoule is 1,000 joules. So I put the 1 kilojoule on the bottom so that the kilojoules will cancel, and the 1,000 joules on the top. So my kilojoules cancel, and I'm going to get 68.1 times 1,000, that's 68,100, and my units are joules per mole. And so now my units will be consistent. And so now I can plug this in here. I can plug everything in. So again, delta G equals delta G standard minus RT ln Q. So delta G standard, we just found it out here, 68,100 joules per mole. R, 8.314 joules per mole per Kelvin. Temperature was 298 Kelvin or 25 degrees Celsius given in the problem. And ln Q we already calculated was a negative 11.51. Notice here that kelvins are going to cancel, and we're going to get joules per mole. So, and I'm just going to write that here. So my kelvins are going to cancel. Oops. Kelvins cancel. Whoop, whoop. And my units here are joules per mole. And my units here are joules per mole. All right, good. So my resulting units at the end will be joules per mole. All right. And we're going to multiply times ln Q, which was 11.51. Okay, so let's calculate this now. It's going to be 68,100 plus 8.314 times 298 times negative 11.51, and that equals 39,583. This is going to be good. The last sig fig here is the 1, so this is going to be good to where the 5 is. So we should write this as 39,600 joules per mole, because the last sig fig here is going to be at the hundreds place there. Okay, and we could convert this to kilojoules per mole if we want. It would be 1,000 times smaller, so it would be 39.6 kilojoules per mole. Either answer is correct. Often delta G's are given in kilojoules per mole because obviously that's a more convenient number than joules, but both of these are correct. And that's how you find the delta G given the delta G standard, which you can get from the appendices. You can calculate it based on the appendices, and Q. You can calculate Q. So let's take now often, especially on your ACS exam that's coming up, what they really like to do is, instead of having you do a long and drawn out calculation, they'll ask you, and I will do this too, I'll ask you to interpret how this equation works or what it means. And so if you're at standard states, imagine we're at standard states here. So remember, standard states means 1 atmosphere pressure for all gases, 1 molar concentration for all aqueous things. And so what that means is that if you have Q and you're plugging in 1 atmosphere or 1 molar concentrations for everything in Q, that means Q is going to be 1. And the natural log of 1 is 0. So here, basically, let's think about the relative sizes of these. So if Q is very, very small, okay, if it's far less than 1, we're not at standard states. We have essentially a lot more. We have a lot more reactants than we have products. Okay, remember, just a reminder. Q and K, Q, K, these are, approximately speaking, they are product concentrations or pressures over reactant concentrations and pressures. So if Q is much less than 1, what that means is that the bottom of the fraction is bigger than the top, meaning we have a lot of reactants and not a lot of products. And the result here is that R, T, ln Q will also be will be less than 0. Why? Because if you take if the Q is less than 1, if you take the natural log of a number that's less than 1, you're going to get a negative number. Okay, so basically if Q is less than 1, then this whole term here will be negative, which means that the delta G here will be less than the delta G standard. So in this case, the total free energy decreases as the reactions proceed spontaneously in the forward direction. When the reaction mixture is mostly products, meaning we have a very large Q, that means that's the opposite. So in that case, then in that case, Q is going to be greater than 1. So if we have lots and lots of products, the top of this fraction will be big, the bottom will be small. So Q will be greater than 1. And the result is that this will be a positive number. And so that will make the delta G bigger than delta G standard. I'll make it big. Okay. And delta G will likely be greater than 0. So the total free energy decreases as the reaction proceeds spontaneously in the reverse direction. So what does this mean? This can be explained with a graph here. So this, let's say this is the total free energy of the reactants and products on the vertical direction. And this is the reaction progress. So this is the reaction moving forward. So at the beginning, delta G is less than 0. So this indicates a spontaneous reaction. Remember, delta G less than 0 means spontaneous reaction. So the reaction proceeds forward and the total free energy of the reactants and products is decreasing until it reaches a minimum. If it's past that, so this is the other situation here, where the delta G now moving in this direction is positive. So the reaction will not be spontaneous beyond this point because the delta G will be positive. So here, this reaction moving forward would be non-spontaneous. And equilibrium is right here when we get to this lowest point, the lowest point of the total free energy of the reactants and the products. So this is the standard free energy here of the reactants. It's proceeding forward, making more and more products, and we have the sum of the delta G standard reactants and products. When that reaches a minimum, that's where you have equilibrium. The reaction will not be spontaneous past that. And this is indicating the delta G standard for the reaction, the difference between the delta G of the reactants and the delta G of the products. So the delta G standard here is negative for the reaction, but the delta G of the reaction depends on how much products or reactants you have. And when you get to the right ratio of products and reactants, you have a minimal total free energy for reactants and products. And that is the point at which the reaction no longer is spontaneous in the forward direction and you are at equilibrium. Now let's talk about the relationship to equilibrium here. Okay, so as I said, if you are at the standard state, that means that Q is equal to 1. Why? Again, Q is the products over the reactants, just generally speaking, products over reactants. But remember what standard state means. Standard state means that all of the concentrations or pressures of products and reactants are equal to 1. And so that would mean that this quotient here would also be equal to 1. So if that is equal to 1, the natural log of 1 is 0. And at that point, delta G equals delta G standard. Now, another situation that occurs is when delta G is 0. So that's what we just discussed previously. When delta G is 0, we said that is equilibrium. And so Q equals K at that point. And so if delta G equals 0, what we're going to do is plug in delta G as 0 right here. And we're going to plug in K for Q, because at this point when delta G is 0, that means we are at equilibrium. So that means 0 equals delta G standard plus RT ln K. If we subtract or add our negative RT ln K to both sides, that cancels these here, and we get delta G standard equals minus RT ln K. So there is a relationship between the standard delta G and K, the equilibrium constant. It's minus RT ln K. So now let's analyze this equation here based on K. Okay, so if and its relationship to delta G standard. Remember, delta G and delta G standard are different things. Delta G is 0, that's when you're at equilibrium. All right, that's the minimum right here. Going back to the last slide, this is delta G is 0. Not delta G standard, but delta G is 0, right? And so in delta G 0, we're at equilibrium, so Q equals K. But how are delta G standard and K related? Well, they're related based on this equation, which we just derived. And let's start here with delta G standard is 0, the bottom part. When would delta G be standard be 0? It is when K equals 1, because the natural log of 1 is 0. And so delta G standard is 0 when the natural log of K is 0. That is true when K is equal to 1. Again, great question that commonly occurs on standardized exams about chemistry. Here to see, do you understand how to interpret this equation, not just punch numbers? Now, what if K is greater than 1? So K equals 1. If K equals 1, natural log of K is 0, so delta G standard is 0. What if K is less than 1? If K is less than 1, then the natural log of K is a negative number. And so this whole part will be positive because you'll have the negative of a negative number. So delta G standard will be positive. If K is greater than 1, then the natural log of K will be a positive number. So you'll have a negative times a positive. You'll have a negative number for delta G standard. So delta G standard will be less than 0. It's important that you can not only plug in numbers correctly, but understand how to interpret these equations. Remember when I told you, knowing that the natural log of 1 is 0, and the natural log of a number greater than 1 is positive, and the natural log of a number less than 1 is negative, will be very useful to you. It's for situations like this. So here, again, if equilibrium constant is 1, natural log of that is 0, so delta G standard is 0. If equilibrium constant is less than 1, then the natural log of K is negative, less than 0. So delta G here will be negative times negative. It will be positive, greater than 0. If K is greater than 1, then the natural log of K is greater than 0, which makes this whole right term negative, making delta G standard negative. And what does this mean? Well, if K equals 1, that means at equilibrium you have equal amounts of products and reactants about. If K is less than 1, that means you have more reactants and less products. The bottom of the fraction is bigger here. If K is greater than 1, that means at equilibrium you have more products than reactants. And so that's another way of translating delta G standard. When delta G standard is 0, that means the equilibrium constant is about 1. When delta G standard is negative, that means the equilibrium constant is greater than 1. When delta G standard is positive, that means the natural of K, or sorry, that means the equilibrium constant is less than 1. Okay, so given this equation, delta G equals minus, or delta G standard rather, equals minus RT ln K, we have a new way that we can calculate K. And this new way is if we know delta G standard, we can calculate K. So to calculate K for this reaction, this is a common question. Calculate K for this reaction given what you have in the appendix. So we can get the K by calculating delta G standard and looking up the delta G standard of formation values. So to find the delta G standard for this reaction, we take the delta G standard of the product calcium oxide solid plus the delta G standard of the product carbon dioxide gas, and subtract the delta G of, and these are formation values, sorry, subtract the delta G standard of formation of calcium carbonate. And so we would of course go and look those up in the appendix. So you go to the appendix, look them up. If you look them up, you'll get these values. The delta G standard formation for calcium oxide is negative 603.3 kilojoules per mole. For carbon dioxide gas, it is negative 394.4 kilojoules per mole. And subtract the delta G standard formation calcium carbonate. If you look that up, you'll find it is negative 1129.1. So we now can calculate the delta G standard of the reaction. It's going to be, we're going to add these two first. So negative 603.3 minus, or I guess it's equivalent, we could say plus a negative, same thing, plus 394.4, close the parentheses, we need to add these first, and these are both 1 times those because all the coefficients here are 1, and then we're going to subtract negative 1129.1, and that gets us 131.4 kilojoules per mole, positive 131.4 kilojoules per mole. So now we have the delta G standard for the reaction. We can use delta G standard equals minus RT ln K to figure out the K. So I'm going to carry this amount forward. Delta G standard is 131.4 kilojoules per mole. We need to calculate the we're going to determine the natural log of K, and then we're going to determine K. So for delta G standard, let's solve this for the natural log of K here. So we divide both sides by negative RT, and so these cancel here, and we get natural log of K equals negative delta G standard over RT. Okay. And now we can plug in our values. We'll plug in the negative here. The negative is right here. The delta G standard we got from the last slide, 131.4 kilojoules per mole. R is our standard thermodynamic gas constant, 8.314 joules per mole per Kelvin. Temperature is 298 Kelvin. And we're going to convert joules here to kilojoules, because we need to make sure that the units are consistent. So notice here that joules will cancel with joules, kelvins will cancel with kelvins, and on the bottom we're going to have kilojoules per mole. So our units are going to divide out. So here we have kilojoules per mole on the top, that's going to cancel with kilojoules per mole on the bottom. So all our units go away, which is expected because we're calculating a K, which are generally unitless. So now all we have to do is plug the numbers in, and so we get negative 131.4 divide by 8.314. Put this up here. And then also, remember, these are all on the bottom, so divide by all of them. So also divide by 298, and then we're dividing by 1,000. So that's the same as multiplying by 1,000 times 1,000 equals. And we get natural log of K is negative 53.04. Negative 53.04. And now we're going to take the anti-natural log of both sides. So we're going to do e to the both sides here. E to the power, which will cancel the natural log, and e to the power here. Okay, so we're going to do then, we'll hit shift, and then natural log, and then answer. and we get 9.3 times 10 to the minus 24, or 9.3 times 10 to the minus 24. I think because I didn't round in between, I got 9.3 instead of 9.2, but same thing. So that's how you determine the equilibrium constant from the delta G standard. And that's the last thing for thermodynamics. So we have now completed the chapter on thermodynamics. Next, we'll be moving on to electrochemistry. So in this chapter, we have discussed the free energy formation, delta G. We have calculated the delta G standard from appendix values of delta G of formation. We have also used that to calculate the non-standard delta G of a reaction using delta G equals delta G standard plus RT ln Q. And we also used delta G standard equals minus RT ln K to determine the equilibrium constant for a reaction. And I'll just give you these parting words. Notice that I showed my units in every single calculation. You need to do the same, okay? Especially in the ones where you write down and show me your answers. Why? I'm doing it for you. I'm doing it for your success. If you get in the habit of keeping your units, you will avoid problems where you don't have the right units because you will notice that they don't cancel correctly. So that's my last parting words to you if I didn't say it enough times already. And I'll see you in the next video on electrochemistry.